All right, let's take a look at Achieve number 10 in section 3.10. This is again related rate section. And I wrote down the information from the problem. Again, you have to carefully read through everything and make sure you understand what's going on. So in this case, at a given moment, you have a plane that passes directly over a radar station at an altitude of 7 kilometers. The plane speed is 800 kilometers per hour. And let H be the variable that represents the distance between the plane and the station, through the air. And then there's two parts. How fast is the distance between the plane and station changing half an hour later? And then basically the same thing. How fast is the distance between the plane and station changing when the plane passes directly above the station? Okay, so let's talk about setting this problem up. I would draw a picture again. 99% of the time on these problems, it's a geometric type of problem. You want to draw a picture a lot of times to get things straight. So I've drawn a picture with my radar station here. Here's the ground. A point directly above the radar station that intersects with the flight path of the airplane, which, by the way, is flying at a height of 7 kilometers. So we're assuming then it's not going to change its altitude. It's going to remain fixed. Again, I know ground goes up and down. Don't worry about that. We're just going to assume that, the ground level is right where the radar station is. Okay, so a couple variables. They give us one variable, the distance between the plane and the radar station is H. It says that the airplane passes directly over a radar station. So at this point, it's directly over. So I'm going to assume some time has elapsed. In fact, in part A, how fast is the distance changing between the plane and the station half an hour later? So half an hour after the plane is at this point, it's, over here somewhere. So the plane is flying at 800 kilometers per hour. I do want a variable to represent the distance from this point directly over the radar station to the airplane. I'm calling that distance X. And that is, of course, changing. In fact, the rate of change of X is exactly equal to the velocity or speed of the aircraft. X is getting bigger, right? That distance is increasing here. So I'm given that dx dt is 800 kilometers per hour. We're asked to find dh dt, right? That's the distance between the plane and the station. Okay. Notice right away that H is getting bigger as the plane flies further away. So you would expect dh dt to be positive. Okay, what's the relationship between our variables of interest here, X and H? Well, I think we've seen Pythagorean theorem so many times. I hope we see this right triangle. We're going to assume that's a 90-degree angle because the plane again is flying at a fixed altitude of 7 kilometers. So the Pythagorean theorem says this side length squared X. What's this side length? Remember, that's the same as the height of the airplane. The altitude is 7, and then the hypotenuse. So the sum of the squares of the two sides is the square of the hypotenuse. And so I'm going to take the derivative with respect to time of both sides of this equation. Remember, X and H are functions of time. So when I take the derivative of X squared, it's chain rule. Derivative of the outer function is 2X, bring the 2 down, right, subtract 1, times the derivative of the inner function, which is X with respect to t, which is just dx dt. Derivative of 49 is 0 because 49 is a constant, not changing. Again, that altitude is not changing, so the rate of change of the altitude is fixed. And then the derivative with respect to time of h squared is 2h dh dt similarly. So here's our related rates equation. I can solve for dh dt by dividing both sides by 2h, and I get dh dt as x divided by h times dx dt. And dx dt we know is 800. I could even replace, that and write this as 100x divided by h if I wanted to. Okay. Now, there's our, now we can plug in, right? This is the rate of change, and we want to find it at particular instances. Half an hour later, what do we know? Well, the plane is flying at 800 kilometers per hour. So if I multiply that by 1/2 an hour, I'm going to get 400 kilometers. Okay, so in half an hour is going to get 400 kilometers. Okay, and also that's the value of x is 400, therefore half an hour later. What about h? Well, we know this relationship here. So if I replace x with 400, I can solve for h, which I've done here. H is the square root of 160,049. So now I can plug in, right? DHDT right here is X, which was 400, divided by H times DXDT, which is 800. So evaluating that gives me the 799.878 kilometers per hour. Be careful to read. They do say give answer to 3 decimal places. You want to make sure you do that. Don't round any intermediate results until this final result too, so that you don't have any rounding error. Part B says, what's the rate of change of the distance between the plane and the radar station when the plane is directly above the station? Well, if it's directly above the station, we go back half an hour earlier, X is obviously 0 if you're directly above the radar station. And if and H is just at that point, the distance is just the altitude, right? Exactly over is going to be 7 kilometers. So X is 0, H is 7. If I plug in those values, of course, what am I going to get? 0 times anything divided by anything is 0. I get 0 kilometers per hour. So that instant, that rate of change is 0. In fact, before the plane passes over the radar station, if we had a problem set up like that, then the distance from the plane here to this point directly above the radar station would be getting smaller, and our DHDT and the DXDT, by the way, would be negative, right? It would be negative. DHDT is negative until right at this point it's 0, and then it's positive. Okay. In fact, that point, the derivative being 0 and the plane is the closest to the radar station at any point in its flight path, that's a very important problem. We're going to be looking at optimization problems later on. I also wanted to look at, it's kind of interesting that half an hour later, here's this rate of change of the distance from the plane to the radar station, and that's pretty darn close. I mean, really, rounding off to the nearest kilometer per hour, that's exactly the speed of the airplane. So what's going on there? Well, if I just, little aside here, so that's the end of the problem, but a little aside, if you come up here and you solve for H, notice if I take the square root of both sides, I get H is X square root of X squared plus 49 from this equation. And if I replace H with that, and DXDT, remember, was 800. So I have 800 times X divided by H, which I'm replacing it with this. Here's DHDT. Well, go back to when we talk about limits. As T goes to infinity, X goes to infinity, right? X is getting bigger and bigger as time progresses. This plane begins to continue to move out that way. Well, as X goes to infinity, see if you can recall how to find limits at infinity, but you should note that as X goes to infinity, this expression is going to 800. In other words, as time progresses, the DHDT, the rate of change between the radar station and the plane, is approaching, getting closer and closer to 800 kilometers per hour, the actual speed of the airplane. And you can see half an hour later, it's almost, practically there, right? But it continues, that rate of change will continue to increase, but obviously not much very rapidly. So obviously initially it does so very rapidly, right? Because it's 0 kilometers per hour, right? And when the plane is directly over the station, half an hour later, it's already 799.878 kilometers per hour. So just some interesting interactions. You can see how calculus helps you to analyze these problems, and also how radar stations really work and how they can determine the actual speed of aircraft, right? They can measure this DHDT, and based on that, they can determine the DXDT. So this problem is given DXDT, find DHDT. Radar station problems is given DHDT, find DXDT, and it can be done similar to what we did here. Okay, fun problem. Love airplane problems. Hope this helps. Let me know if you have other questions.